So I'd like to talk about a very simple circuit. In fact, so simple most people just go, oh, it's no big deal. This is a current mirror. And current mirrors are used like everywhere in analog circuits. And I love talking about this from a MOSFET perspective because in MOSFET perspective, I don't have to worry about any leakage out of the gate. So I can make multiple copies and replicate at least in a steady state solution everywhere. And at its very core, it's a case of I initially take this input voltage, it sets up a feedback such that that voltage node V finds the steady state such that this transistor M1 sinks that current and pulls that current down. And then you put the same element, M2, and we're going to consider them to be identical for the moment, will then allow you to pull. It means I put the exact same voltage that pulled that current, so I should get exactly that same current. And that's awesome. Now, if I'd like to scale that current by a factor of 2 or 4 or some number, I simply need to scale the W over L ratios of M2 and M1. Another easy way to think about it. Imagine if I had two M2s and I tied them together. I'd imagine the current is double. You're like, yes, that makes sense. If I had 4 of them, it would be 4 times. And in more subthreshold, super scaled down processes, that's all you get anyways. So it works, right? It's kind of what you'd expect for these devices. Now there's a slight shift in there, because if you assume that sigma equals 0, well, then it solves a little bit easier. But again, here's what the transistor curves look like in assuming sigma's there. Now, if sigma's 0, I out just becomes I in, and you're like, yay! Now, if sigma's not 0, this is going to change a little bit. And so that's something you would look at in terms of dynamics. And so you can see a little bit of a shift, and you're still going to see things like limitation of gain if you're using a current mirror to load into another transistor. On the other hand, it's going to be fairly good, and you can kind of work with these devices. It's really pretty neat that I can just make copies wherever I need to. And so and I can make scaled copies. And so, yay, this is a really good feature. But on top of that, now you ask a different question. And now you begin to ask the question, what happens for the dynamics? And this is something that most people are not usually thinking about in terms of the overall behavior. Dynamics means that looking at the capacitance on this node, and you have to have a capacitance because there's no way you're not going to get capacitance at some fixed potential. So, okay, fine. And let's actually look at the dynamics with sigma equal to 0, because we could talk about the dynamics with sigma, but I think that'll just complicate the picture. So if you look at that, then it turns out to be fairly straightforward that the current on this node, right, is going to be a couple things. And here's what's interesting. It's going to be the input current here minus the current sunk by M1. But immediately you're going to go, wait, the current sunk by M1 is M2. It's I out. And so I could have written this in this form as well with the UT. So these are equivalent definitions with sigma equal to 0, right? Just kind of think about it here for a second. Right? That would be its kind of steady. You get the same expression. And you think, okay, this is probably a little bit more palatable to work with. But something interesting happens along the way. The thing interesting happens along the way is you realize, well, what happens if I just compute the derivative of I out? Well, I do have an expression for I out. In fact, it's right here. And sigma equal to 0, I out, it looks like this. Well, take the derivative of it. Well, di out then it's an exponential. So what's cool about exponentials? It's the same thing plus just what's the gain in the exponential. And you're like, oh, okay, so that means it's just I out times a kappa over ut. There you go, times the derivative of v versus with time. Because remember, you're not sure what that is, right? In fact, it's probably going to shift, and you're like, oh wait, is that a way to handle this? And now I can put this expression and this one together, and I get one set differential equation. And you look at this equation and you think, wow, this is pretty cool. All these exponentials gives me something in a polynomial form. And you could linearize this out at around a particular bias point, and you get very nice linear dynamics. Nice linear dynamics that would be basically relative of where a time constant would be CUT kappa over that bias current, right? Because if I out was nearly fixed, let's call it a bias current, and then this just looks like a very simple linear system, and everything is easy. It's straightforward as a low-pass filter. And yet, here's the question. Even in the nonlinear dynamics, it's a pretty fascinating problem. So here's something to think about. Imagine I was to look at this circuit now and look at this for different step responses. And I'm going to look at it for sort of smaller, I'm going to look at it in sort of the linear scale and the and sort of log scale. And I'm going to look at steps, and I'm going to look at steps going from a particular point, but I'm knowing that my equilibrium is going to want to go to 10 microamps. Okay, that's where the output current is. So my input is going to be a step from a particular point to 10 microamps. It might be from 20 nanoamps, 5 nanoamps, 1 nanoamp, 100 picoamps, and 10 picoamps. And you look at the dynamics and you think, wow, this is actually quite different. And actually quite a neat sort of structure. If you look at this closely, these are actually exponential functions. For example, hyperbolic cinches and related stuff. And the lower ones are actually tanh functions. So it turns out you get something that's roughly an exponential, rising exponential, and then it falls off. And so you can kind of see the tanches for those who are used to seeing those kind of curves. Really fascinating curves, but it's like starting like part way through the tanh. And so here's the thing, when you're looking at higher currents, you can see them all come here and converge into 10, or the lower currents that get a strong exponential converging in and then eventually flatten out. And this is, again, this is now looking at log of output current going towards equilibrium. It's a very strong dynamic, but there's also a strong delay in each of these cases. And this becomes very important. And you might go, well, why does this show up? Well, why is this important? Well, it turns out that the current mirror is a prototype for almost all of the dynamics you get with exponentials and capacitors. This is what you see in large signal all the way through. And understanding these dynamics are essential. Whether you're talking about typical integrated circuits, whether you're talking about something that may be neurobiologically inspired, whether it's coming from some other physical system, if you're actually modeling neural physics, you're going to see this show up again and again. In fact, the first place where I saw these dynamics looked at carefully was conversations with Corbin in sort of 1992-93 when he turned 92-93 when I actually got to take sort of analog VLSI and neural systems at Caltech, and he was running the course, and he threw a lot of this conversation at us. You'll find almost none of this published. That's just kind of how that goes. So much of this, though, gives you kind of good insight to what these dynamics look like. And this is why I wanted to kind of make sure that this is all on a good foundation so that we kind of get a sense of there's a lot of richness to what looks like a very, very simple little circuit.